Hi everyone. In this video, I will cover the discussion of the physical properties for the material cyclic CP. So that is given here. So let's rename it with CYC and IQCP cyclic elastoplasticity model with cutting plane algorithm, and we'll discuss some parameters here. So the first one, let me just first tell you about the model. Uh, this was covered previously in the previous lecture. This research paper, the large post liquefaction deformation upside part one physical mechanism, constitutive description and numerical algorithm cover the parameters of this soil model, and the ranges are already given for this side in this table number one here. So just in case if you are wondering about the nomenclature, so you can use these in your analysis file here. Um, and the purpose of this model is to simulate the behavior of material that is particularly soil and the specific conditions related to forced liquefaction deformation, which is when soil behaves like a liquid due to shaking during events like earthquakes. So this model is nomenclature that is CYC stands for cyclic, LIQ stands for liquefaction, and CP stands for clay plasticity model here. So this is a elastic plastic model that also undercovers the cyclic deformation in the model with the plasticity. So the main features of this model is cyclic elastoplasticity, which means that the material can undergo both elastic recoverable and plastic permanent deformation or cycles of loading and unloading. And this model has a large deformation capability. It can handle large deformations ranging from small to large, which is crucial for accurately modeling liquefaction scenarios, and also for pressure-dependent elastic modeling. The stiffness of the material change with the applied pressure. Another feature for this model is this model has bounding surface plasticity, which, in the other words, is the permanent deformation. It is modeled within the framework that consider limits on how much a material can deform plastically before failure, and also this model has reversible and irreversible dilatancy. The dilatancy basically refers to tendency of the material to expand when subjected to loading. The model account for both reversible that are temporary and irreversible that are permanent dilatancy effects. There are some sort of limitations for this model. The first limitation is the state of sand. This model does not consider the specific state of the sand, which means it's required different parameters for sand under various densities and parameters, and also for surface representation, the surface like failure and maximum pre-stress are represented as circle in a specific mathematical plane that is required for it here. And regarding the usage of this model, so this model has been tested and validated against experimental data from centrifuge test on model test. You can study about literature for this, and it has been used in various simulations related to liquefaction problems, indicating it is applicability and reliability in its nature. So when used with regular solid elements like four-noded quartz or bricks element, the model simulates the response of drained soil, which means that the soil where water can flow freely And when coupled with soil fluid elements like UP elements and SSP UP elements, it can be simulated undrained and partially drained soil behavior, which means that it can model simulation where water flow is restricted or only partially allowed. And to material behavior control, it's to control and account for the effect of gravity and static loads initially. The material behavior is set to linear elastic, so this is done to simulate the initial response of the material to these loads. And after the initial stage, material behavior is updated to achieve the desired elastic plastic stress strain response, allowing for more accurate representation of the material behavior under cyclic loading conditions. So, cyclic CP is a sophisticated model tailored for simulating the complex behavior of soil, particularly in scenario involving liquefaction where soil behaves like a liquid due to external forces like earthquakes. So its capability include handling cyclic loading, large deformation, and pressure-dependent behavior in the analysis. So this paper has those ranges of parameters that we can use uh, in analysis. So let's edit these parameters to use them. And for example usage, I will use these parameters from the table present here. So for different relative densities, we have these parameters, and we can use these in our model for the specific. Sorry. So we have this G naught parameter. We can use it in range of 100 and 200. We have the kappa value, which is 0.001 and the range of 0.1. Then we have the parameter h, and which is 0.7, and model parameter for plastic model. It is then we have MFC of 1.4 stress ratio to triangle compression. These are constant values. For DRE1, we have 0.4 coefficient for variable reversible diluency generation, and we have MDC that is zero point 0.3, and we have DRE2 that is 1000, and we have our DR value here. Differential strain limit, we can use it, for example 0.01. We have then alpha parameter, which is missing here, and RDR, it is missing here. We have DIR, that is missing here. We have EIN, that is also initial wide ratio, so we can consider it 0.45, whatever it is for the parameters. And if we consider the saturated mass density, so we need to define the saturated mass density. We can calculate this from the geotechnical equations um, for the model. So all the details are given in this research article, just in case you want to understand in a more detailed way about the parameters for this cyclic material elastic plasticity model. So this is for the cyclic plasticity model, and we have this another in the material cyclic CPSP model. So again, the parameters are same except some parameters uh, NP, INART, and all these parameters are required to mention in this model. So let me continue discussion on this model in the next video. Thank you so much for watching.